let us start the seminar. Before starting, let me briefly introduce today's speaker. Today's speaker is Professor Ranjan Laha from Indian Institute of Science. He received a PhD from Ohio State University at 2014. And after that, he experienced a postdoc at Stanford University and Kabul Institute for Particle Astrophysics and Cosmology and Mainz University, SAN, until 2020. And since 2020, he has been a professor of Indian Institute of Science. So today, he's going to talk about detecting low-mass primordial black hole as a dark matter candidate. So Ranjan, please start your presentation.
Okay, all right. Okay, thank you very much for everybody for attending the talk. I hope all of you are doing well and your family members. So today I'll be talking about some of my recent work on detecting low mass primordial black holes as the dark matter candidate. I will define low mass slightly later in the talk, right? Once I come to the main part of the talk, right? So this work has been done in collaboration with lots of people who are named here, all right? And they taught me everything about this work. As usual, if you have any questions at any point of the talk, just feel free to unmute and ask me. Right? I'll be happy to answer. Okay, so if there are any young students, let me give you a very brief introduction to gravitational detection of dark matter. Dark matter has been detected gravitationally for many years, for in fact close to 100 years. If you count Zwicky, or even if you count earlier, it's even more than 100 years. So the way I look at it is, if you make various astrophysical observations at various length scales of the universe, you would require dark matter to solve it, right? So let me explain these one by one in a brief detail. So what is plotted in this? This is the rotation curve of a galaxy, NGC 6503. All right. So rotation curve means you look how the stars are rotating around the center of the galaxy. All right. So stars or gas. All right. So rotating. What is plotted is that on the x-axis is the radius from the center of the galaxy. On the y-axis is the circular velocity. So this is square root gm over r, so 0th order, right? It's not nothing. And these are the data points, right? You can see the data points here, right? If these data points are due to the gas in the galaxy, the V circular would follow this line. If it was due to disk, right, the material in the disk, right, it would follow this line. However, it turns out that if we add these two, gas and disk, it does not match the data. There is a factor of 5 uncertainty, roughly. Sorry, factor of 5 difference. You require additional mass in the form of the halo component, all right, the component, which is basically a spherically, roughly spherically symmetric, roughly spherically symmetric object made up of something which we call dark matter, which encompasses the galaxy, the visible galaxy. All right. Once you add the halo component, you get a nice fit. All right, and this is true not just for this galaxy, for many galaxies, even for the Milky Way. So this, I claim, is the detection of dark matter at scales of 10 kiloparsec, roughly. All right, you see these are 10 kiloparsec. So let's observe at a slightly bigger length scale. Let's observe the length scale at 100 kiloparsec. So now consider on this thing. This is an artist impression of the picture of the Milky Way side on, right? So if you're looking at the Milky Way side on, this is what this looks like. This is the galactic center. This is the galactic bulge, and this is the galactic disk. All right, and you see small things. So this is a large Magellanic Cloud, small Magellanic Cloud. These are small satellite galaxies, and there are even smaller satellite galaxies. All right, some of these. So these satellite galaxies have some motion, all right, and that motion can only be understood if we assume that there is a dark matter halo, spherically symmetric dark matter halo around this object, right, around the visible galaxy. All right. So these objects are roughly 100 kiloparsecs away, very roughly. So this is the proof that you require dark matter at scales of 100 kiloparsec. So let's go to a bigger scale, right? So this is a very famous picture of a bullet cluster. So bullet cluster is basically thousands of galaxies bound together gravitationally, right? Sometimes these two galaxy clusters merge, right, or they collide. So let's see what happens. So obviously, galaxy clusters have stars, and stars do not collide among themselves, right? Because the distance between two stars is much larger than their radius, right? So they almost never collide. So they just go straight through. There is gas, and the gas actually collides, right, because of strong electromagnetic interactions. So this is this part, this pink region, right? And if there is dark matter will go straight through it. All right. So this is the region where it's dark matter, which is basically observed by lensing. Right, this blue region. Right, you lens the background galaxies or the stars, and you observe this. You see that there's most of the mass is here in the blue region than in the red region. All right. And one thing to note is this is not the only cluster that we know, colliding cluster we know. Roughly, if I remember correctly, the last time I checked, there are roughly 70 clusters which are merging. Right, so this is nothing anomalous. Right, and in all of them we see that the proof of dark matter, the fact that there is extra matter which is not seen by electromagnetic radiation. All right, so that's the definition of dark matter here. So this is happens at a scale of say megaparsecs. All right, so this is the proof that there is dark matter at megaparsec scale. Okay, let's go to the bigger thing. So this is at gigaparsec scales. So this is CMB. So CMB is basically the ancient light, and if you want to understand the CMB, you require some part of dark matter, right? Universe, which is roughly whatever 27%, right? 5% of ordinary matter, and remaining 69% or whatever is dark energy. Right? This is very precisely measured. Right? This is known to a percent level, dark matter density. The ordinary matter percentage is known to a sub-percent level. Right? So these are the energy densities. Right? So this happens at a gigaparsec scales. So I gave you 4 examples. Right? And these are not the only examples. There are also other examples from kiloparsec scales, hundreds of kiloparsec scales, to megaparsec scale, to gigaparsec scale, where you require dark matter to understand all astrophysical observations. Okay. Now, suppose you are more theoretically minded and you said, well, okay, let me try to see if in theory I can get dark matter. All right. So what you can do is you can try to run a simulation. All right. So you can run the simulation of the whole universe. People can do that nowadays. And this is one of the pictures from the illustrious simulation, right? This one. So the left-hand side is real observation of a patch of the sky. The right-hand side is a mock observation from the illustrious simulation. Right? This is available in the illustrious website. So this is one of the most latest cosmological galaxy formation simulations. And you can then do a mathematical, like whether it's whether these two sides are equal or whether they're equivalent or not, and they're actually equal, right? So there are lots of papers trying to compare the real observation with these mock observations from simulations, and they match. So this tells you that even if you want to form galaxy formation theoretically, there must be something called dark matter, right? So the dark matter must be something out there, right? Some extra matter that is out there beyond what we know, right? So this is what I say is a theory proof of dark matter, right? So although we have lots of astrophysical proofs of dark matter, funnily, we have no proof of what it is made up of, right? So the smallest object that a dark matter candidate can, so smallest mass that dark matter candidate can have is roughly 10 power minus 22 eV, all right? And then it can also be as heavy as roughly 100 solar mass, right? So this is a wide range. This is 80 or 90 orders of magnitude, right? And I think it's important to thoroughly test all well-motivated candidates in this mass range, right? In principle, more precisely, it is important to test parts of the parameter space where a given candidate can make up 100% of the dark matter density, right? Now I know that human works a lot on dark matter, various particle dark matter candidates, but this time I will talk about dark matter candidates which are not made up of particles, but which are made up of macroscopic objects, right? Sorry. Okay. So this is this was the brief introduction. So now I'll come to the contents of the talk. So I'll talk about very briefly introduce primordial black hole. This just the introduction can take up a whole talk, all right? So I will just be very brief. I'll talk about what parts of the parameter space primordial black holes can make up 100% of dark matter density. And then I'll talk of 3 related works where you try to constrain the primordial black hole density due to Hawking radiation, all right? First will be the measurement of galactic center positrons. Second will be the measurements of galactic center photons. And third will be some future projections. And then I'll tell you what are some other works, just in one brief slide. If you're more interested, we can talk. And then I'll conclude. Is there any question till now? Maybe since I start. Okay, it's going on. Good. So what is the primordial black hole? So primordial black hole is one of the earliest dark matter candidates. It was first discovered by Zeldovich and Novikov in 1966, right? And then Hawking took it over. In fact, if you read Hawking radiation papers, he got interested in Hawking radiation because of primordial black holes, small primordial black holes which are smaller than that, right? I'll tell you what exactly is a primordial black hole. The first mention that primordial black holes can be dark matter was in this paper by Chaplin, which is published in Nature, 1975. That was the first paper, as far as I know, which mentioned that primordial black holes can be dark matter. Okay. So what are primordial black holes? So primordial black holes are exotic compact objects. These are black holes which form in the early universe, either due to some large density perturbations which come from, say, inflationary models, or due to some other kinds of new physics. All right. In fact, currently, like almost there's a new paper on primordial black hole formation every day in archive now, right? Because of this LIGO discovery, there's been a huge revolution of how to make primordial black holes, right? There's one paper every day. So I mean, but the important thing is that whatever you do, primordial black holes always require new physics, right? So if you find a primordial black hole, and this is the point I will emphasize later also, which does not make up 100% of dark matter density. Suppose it makes up 1% of dark matter density, then it's new physics. That's it. It's a guaranteed new physics. There's no way astrophysics can produce primordial black holes. Right? There's zero chance. Right? This is very well known. Right? So that's why the connection of primordial black holes with BSM physics. So in many of the models, you can connect the primordial black hole mass MPBH with the time when it is formed. Right? For the simplest inflationary models, this is the thing. So a primordial black hole which is formed at 10 power minus 23 seconds, all right, in the universe has a mass of 10 power 15 grams, right? Now this expression is not true for all models, right? This varies, but it's always true that primordial black holes, especially low mass primordial black holes, are formed at very, very early times, right? So that's another motivation. If you find again a single primordial black hole in the universe, that will let you probe the universe at time scales which has never ever been probed, much before BBN. Right? Remember, BBN is the earliest time where we can probe the universe. If you find a primordial black hole, that is probing even earlier than BBN. Right? Few like as fractions of seconds. Right? This is another motivation to learn or to research our primordial black holes. And primordial black holes can have a wide range of masses. Right? I mean, it can have, yeah. I mean, people talk of primordial black holes which cannot be dark matter, right? But still they are just interesting, right? So Planck mass objects to objects which are 10 power 5 solar mass or even larger, right? There's a huge range, right? The dark matter range is not that wide. I'll come to what is the dark matter range, right? And in case if you're not just for a revision, one solar mass roughly is roughly 10 power 30 kilograms, and that is roughly 10 power 57 GeV, right? So PBHs in this formation mechanism, it also tells you what is the mass function, right? So that means which tells you the number of primordial black holes per unit mass. So these are things which come from basic the formation mechanism, either inflation or some other new physics, right? And these mass functions can be power law or even log normal, and they can have a wide range of spins, right, at birth. Right? Again, these are things which comes from the formation mechanism. What is the spin of the black hole? What is the mass of the black hole? All right. Okay, depending on formation mechanism, we can have various different things, right? So
I have a question.
Yes, sorry, yeah.
From my memory, I heard that the black hole generally can form from object to then objects that mass have then one time pole of sun mass.
Yes, good. Yes, so that, yes. So let me just explain to everybody. So the question is, so in astrophysics, we know that astrophysical black holes form from collapse of stars when stars die, and the minimum mass of those black holes is roughly 1.4 solar mass, 4.52 solar mass, roughly, very roughly. That is the Chandrasekhar limit. Primordial black holes can have any mass. Remember, primordial black holes are not coming from star deaths. So this is coming. So the very rough idea. Let me give a very rough idea. Is say due to something in the new in the early universe, there is a very high density in a small mass length scale, right? That collapses. Right. Suppose the density is high enough, that collapses and forms a primordial black hole. That's the formation, right? That has nothing to do with star deaths, supernova. All right. Hence, it can have any mass possible. Right? Obviously, there are constraints, but technically it can have any mass because remember, inflation, the only way we have probed inflation till now is using CMB, right? And that is at very large scales. right? We have not probed the universe at very small scales. These are small scales, right? So think of one solar mass, right? One solar mass, the Schwarzschild radius is roughly 3 kilometers, right? So we have not probed the universe at 3 kilometer length scales, right? Hence, you can have any mass possible. What you're talking about is astrophysical black holes, which have a mass of greater than, say, 1.5 solar mass, right? Technically, even primordial black holes can have mass of greater than 1.5 solar mass. That becomes, then the question becomes, how to distinguish primordial black holes from astrophysical black holes? I'll not talk about that, but if you're interested, we can talk after the talk, after my talk. Is it okay? Is it fine? Does it answer the question?
I see. Thank you for your clear answer.
Yeah, thanks. Okay, now let's talk about primordial black hole dark matter. So the first thing that you know about primordial black holes, or in fact any black holes, not just primordial black holes, is that black holes evaporate via Hawking radiation. All right. So this is a very well-known thing first done by Hawking. Actually, in fact, this was actually first done by Zeldovich, and then Hawking sort of made it more general. So that means black holes lose mass by Hawking radiation. So if you have a black hole, all right, as it Hawking radiates, it will just lose mass. So you can calculate the lifetime of the black hole to the mass of the black hole, right? And the proportionality constant is cubed. So lifetime of the black hole is proportional to MBH cubed. It also depends on the spin of the black hole, right? But that's a mild dependence, right? So what you can plot is you can plot the initial mass of the black hole on the x-axis, mi, and the age of the black hole in the y-axis, all right? You can make these plots, all right, for various spins, all right? So these are spins. This is zero spin, initial spin, zero spin, and this is maximal spin, right? This AI 0.999. Right? You can make these plots, and you can also plot the age of the universe. That is roughly few tens of 13 gigayears, 13, 14 gigayears. That's this line. And if primordial black holes need to be dark matter, their lifetime must be greater than this. That's a zeroth order constraint, all right? Because we see dark matter now. We see dark matter in our galaxy, which is very close. Within 1 kiloparsec, we see dark matter, right? So that means primordial black holes must exist till now, all right? From this plot, you can easily read off the mass. And the minimum mass of a non-spinning primordial black hole dark matter is 6 times 10 power 14 grams. All right. Note that one solar mass is 10 power 33 grams. So this is much, much smaller than one solar mass. All right. So this is the minimum mass. And as you can see from this plot, if there is a non-zero spin, initial spin of the black hole, the mass increases, but that is very slight, from 6 to 9 at the most, 6 to 9 times 10 power 14 grams. All right. So this is a very well-known result, but it was actually recently again redone using updated inputs by RB of Inger and Sith. Right? So this plot is from their paper. Okay, good. So this is a plot of dark matter, primordial black hole dark matter in 2018-2019. I'll tell you why. Because after this, I sort of actually not just I. There were many people who did the work. So this is become all right. So what is plotted on the x-axis is the primordial black hole mass on the x-axis in solar mass. Right, also in grams here. All right, that's for the x-axis. On the y-axis is the primordial black hole fraction. That means what is the fraction of the dark matter which is made up of primordial black holes? All right, so omega, the density of primordial black holes by density of dark matter. If it is 1, that means primordial black holes make up 100% of dark matter density. Okay. So as you can see, this first of all, this plot is not updated. Right, I'll tell you why I'm not putting the updated thing. And there are lots of constraints. All right, this was reasonably updated. All the most of the changes have been here. The low masses, everything is sort of fine. So anything that you see shaded by this red or pink color, say this part, this Kepler, Macho, Eros, ultrafaint dwarfs, CMB, these are ruled out. Right. So what does this mean? Say for example, you say that one solar mass primordial black holes have to be dark matter. This says that their density cannot be more than less than 10%. Right. This thing. Right? So anything above is ruled out. All these things. Right. So at very low masses, there's this constraint from e.g. Extragalactic photons. Right, I'll tell that what is that briefly. So that also rules it out. There's this white dwarf thing which is shown to be incorrect. Right, so just remove this. And then there were some other constraints. This was shown in 2018, 2019. It was also shown to be incorrect. Right. So currently, the mass range that primordial black holes can be 100% of dark matter density is roughly few times 10 power 17 grams to roughly 10 power 23 grams. Right, sort of depends on a few uncertainties, but it's roughly in that. So there's 6 orders of magnitude where primordial black holes can be 100% dark matter density. That's one thing. Second thing, there are regions of parameter space where primordial black holes can be a large fraction of the dark matter density. Say for example here, right, few tenths of solar mass. It can be as large as 10% of dark matter density. We have no idea what it is. Right. So again, I've not shown all the constraints for clarity. It's very difficult to show it. The plot becomes very, very complicated. And there are multiple revisions, and multiple things. And you can look up these references at the end of this lines, right, which have up-to-date constraints. Right? So as you can see, like even a few months, there are new constraints coming up, right? And people have to just update these things. All right. Okay, good. So let me proceed. So I'll be talking about, yes.
Can you comment on the available region around 10 to the minus 12 solar mass? So where this Subaru limit stop applying,
this
right?
So here 10 minus 12, there's no constraint. That's it, zero constraint. So it can be 100% dark matter. This Subaru thing, okay, so this, as I said, this is an old plot. This has been changed. This stops at 10 per 23 grams. So between 10 per 17 grams and 10 per 20, okay, actually few times 10 per 17 grams, say 4 times 10 per 17 grams to 10 per 23 grams, this is 6 orders of magnitude, but there are zero constraints. Zero constraints. So it can be 100% dark matter density. I mean, there have been some proposals how to probe this, but no constraints till now. We just do not know how to probe it. Right? There's a very controversial, as I said, this white dwarf thing. Basically, primordial black hole getting caught in a white dwarf, and it will inject energy into the white dwarf, and it will make it explode in a supernova. I think this is very, very much disputed. Right? So people don't believe it. So I think it's well known. Like this, roughly a few times 10 per 17 grams to 10 per 23 grams, it can be 100% dark matter density. 10 per minus 12 solar mass is roughly 10 per 18 grams, roughly, up to a factor of 2 here and there. So this is 100% of dark matter. Right? There's no question about it. Okay, good.
Sorry. Is there any simple explanation for the Subaru doesn't giving any constraints for 10 to the minus 11? It seems very drastic.
10 per minus 11? No. Okay. So this is drastic because here actually the initial paper Subaru, they made a mistake. All right. So this sort of obviously is not like this. They just it's a smooth curve. All right. It's just, if you look at this Smith et al. 1910, they redo it. I mean, I'm just giving the older plot because this is sort of at least clean. Right? So yeah, so this is an artificial thing. So this Katz et al. Showed that they had a mistake. So that's why they just cut it off. All right. But if you look at Smith et al., they have a smooth thing. All right. So this is a very artificial thing. But using the smooth thing, that's why I'm saying using the smooth thing is between few times 10 per 17 grams to 10 per 23 grams. Right. This 10 per 23 this time here. So yeah, one has to make a very smooth thing here. And as I said, actually, then you can look up all these papers because they put various updates. Right. Is this clear?
Yeah, thank you.
Okay, thanks. Let's proceed. Okay, so I'll be talking about primordial black hole constraints from Hawking evaporation. Let me briefly give you some of the required things. Black holes, as I said, evaporate, produce standard model particles, in fact, any particle, and these can have observable consequences. Right? A very fundamental result, which was derived by Hawking, shows that the temperature of the black hole, PBH, is inversely proportional to the mass of the black hole. Right? Assuming there is no spin, well, even with spin, this relation is true. Right? Mass of the black hole. Right? So roughly a 10 per 10 kilogram black hole has a mass of 1 GeV. Right? And you can also calculate the number of particles emitted per unit energy by a black hole. Right? So this is almost black body. I'll show you in the next slide why is it not exactly a black body. It's almost a black body. So this depends on the spin of the particle. Sorry, this S is somehow got displaced. The spin of the particle S. This is an absorption probability, or this gamma S. This is the energy of the particle. Right? So this is for non-spinning. For spinning, there is one small modification, but overall it's the same. All right. So the basic idea is basically the way you do this calculation. Right? There's a detailed calculation first done by Don Page. Is basically you calculate the probability of producing a producing a pair of standard model particles in a curved metric, right? Curved metric due to the black hole, and then you calculate the probability for one of the particles to escape to infinity, to tunnel to infinity, right? That is Hawking radiation. That's the calculation, right? So production of particle in curved space-time, extremely curved space-time, and the calculation of the probability of the particle to escape to infinity. That is Hawking radiation. To zero, very simple terms. All right, and this is what is done. First done by Don Page in 1976, and then recently it has been done by RB and Offinger. If you have a code called Black Hawk, which is very updated, and you can look into that. Okay, good. So now comes what I promised. So what is being plotted here is the black hole spectrum, right? So note that in this slide, I have slightly changed the notation just to give credit to the original authors. That's it. So here Q is the total energy of the particle being emitted, right? And M is the mass of the black hole, and all other things are constant, right? H, C, G, and all of these things. So this is mass times energy on the x-axis, right? Log scale. On the y-axis is d2n dE dt, right? The number of particles emitted per unit energy per unit time. Okay. If you plot a black body in this plot, the black body looks like this line, this black body line, this long dashed line. You see that, right? You can see my mouse, right? So it's moving, moving, moving. This is a black body, right? For a non-rotating, uncharged black hole, if you have emission of pions, the spectrum looks like this S equal to 0 line, this solid line. This slightly some curves. This looks like this. If it is producing E plus E minus or spin half particle, this is this short dash line, this one. You can see the thing. And if it is producing a photon, it is this dotted line, S equal to 1. So you see these shapes are very nearly to a black body, but they're not exactly a black body. That is simply because this term, this gamma S term, this depends on energy, and that prevents it from being a black body radiation, exact black body radiation. It's not an exact black body radiation. There is some difference. So people typically say the spectrum closely resembles a black body radiation, but not exactly a black body radiation. Okay. From this, you can also calculate at what energy does the emission peak. All right. So given a mass of the black hole, mass and spin of the black hole, you can calculate the temperature of the black hole, and then you can show that the energy at which the emission peaks is roughly, for spin 0 particle is 2.8 times the temperature of the black hole. For spin half particles is 4 times temperature of the black hole. And for spin 1 particle is 5 times temperature, almost 6 times temperature of the black hole, right? So if you know the temperature of the black hole, you know at what energy various particles emission will peak, right? It's roughly order 1 times the temperature of the black hole. It is very roughly, this is the thing, right? Good. So this is the low mass black hole frontier that I'll be talking about. So what is plotted on the x-axis is the mass of the black hole, right? On the y-axis is the fraction of the dark matter in the form of black holes. This solid line that you see, this solid black line. Yes.
In the previous slide, you compare between different spins produced from Hawking radiation. So
yes.
How does amplitude changes? Overall amplitude is because of the number of states, or what is this?
Sorry, how does what? Sorry.
You not only peak position,
yes.
but also the amplitude.
Yes, yes.
The number of photons, number of states, yes. Number of particles.
Yes, yes. Yes.
Spin 0 is okay. Maybe just the integral.
Yes, yes. This is just
integral. You can get the same.
This is this calculation, all right. In fact, here is the calculation of the probability that I talked about. That you produce, say, a spin 1 particle in a curved space-time, in an extremely curved space-time, and then you calculate the probability of it to escape to infinity. This is basically all of this is produced in this gamma s function. This gamma x is a function of E, by the way, right? And also it is a function of the spin of the particle. It also is a function of the mass of the black hole and the spin of the black hole. There are basically 4 parameters: mass of the black hole, spin of the black hole, spin of the particle, and the energy of the particle. Then you can completely get this thing, right? So you have to calculate this probability, and from the probability you can show that the spin 1 is slightly lower than the spin 0 and spin half. This is just coming from the math. I'm not sure if this is a very deep physics. This is just production of particles in curved space-time, right? Is this clear?
Let me see. Okay, thank you.
So remember, all of these things, these 3 lines are for a single black hole. For the same mass black hole, right? This just shows that there's some difference. There's some dependence on the spin, right? Spin 0, spin half, spin 1. Good. Does this answer the question?
Okay. Yeah. Please continue.
Yes. Yes. So okay. So let's come to this. So this is the mass of the black hole in grams, and the fraction of dark matter in the form of primordial black holes. This black line that you see, this black line, anything above this line is ruled out, right? Due to gamma rays. So what is the story? The story is, if these black holes exist, say there is a black hole of 10 power 15 grams at a density of 100% of dark matter somewhere here, right? Everything else somewhere. Then it will produce so much photons that will overproduce the gamma ray background density that is measured by Fermi, GeV gamma rays, right? That is obviously not allowed. We know that mostly blazars or star-forming galaxies produce it. You can do the full calculation, and you can say that this is the upper bound, right? This black line. So anything above is ruled out. So this was done by Carr et al. All right, and then more recently, the paper actually which got me interested was a paper by Baudard and Chirelli, where they showed that using the low energy cosmic ray measurements by the Voyager satellite. So Voyager is the first satellite which went below the heliosphere, that means below the region where the sun can influence cosmic rays. You can constrain primordial black holes, right? So depending on what is the propagation parameter, whether it's propagation A or propagation B, there's some details here which I'm skipping, and depending on how we constrain the background, right? So these are the constraints, all right? This red solid, red dotted, blue solid, blue dotted. Anything above is ruled out, right? So they showed in this PRL paper that using the Voyager measurement, you can probe new parts of the parameter space. So basically, this part, this is a completely new part which they probed. It was a very exciting result. At least I got very excited. And this is why I thought about this. So this is the old gamma ray burst thing I told you. So forget this, all right? So show to be ineffective. This plot is from Baudard was a bit. You see, they came out in 1807, 03075, and in the same month it was shown that this constraint is old or ruled out, right? So this is a very dynamic things happening, right? So forget this thing, right? Forget this line, right? So this is the constraint, right? You see, it's almost touching 10 past 17 grams, but not exactly touching. If you see this one, it's slightly less than 10 past 17 grams. So this probe, this paper, this Baudard and Chirelli paper, led me to think, well, is there a new way to probe primordial black holes, right? Something which people have not considered. So the first thing I came across is the limits from the measurement of Galactic Center positrons. I'll explain what the thing is, right? So this is first, it was the single author paper, 1906, and then there was another paper with some of my collaborators, right? Published in PRL, both of these, right? So this was for non-spinning, this was for spinning. That's the difference. Okay. So before this, so let me tell you of the instrument that I'll be talking about. I'll be talking about the instrument called Integral. Integral is a hard X-ray soft gamma ray satellite that is still running. It has lots of instruments. It has 4 instruments on space. The important instrument that we'll use is called the spectrometer of Integral. It has an energy range of 18 kV to 8 MeV and a superb energy resolution, 0.1%, order 0.1% MeV. This is like unprecedented. In space, going less than 1% is an unbelievable thing with current technology. And Integral was launched in the late 1990s, right? In 1999. So you can see there's a superb experiment, right? It's still running. It has done lots of things for dark matter, for particle dark matter. It has done lots of things for astrophysics, all right? For multi-messenger astrophysics, and it is also done for gamma ray astronomy and astrophysics, all right? So it's a fantastic experiment, right? There's a huge footprint of what it has impacted, right? Lots of discoveries. One of the main results of Integral, although this is not a discovery of Integral, it's a very precise understanding of it, is the 511 keV gamma ray line. So what is this? So if you have an instrument which is sensitive to 511 keV, and if you look at the Galactic Center, this is what the galaxy, this is what the map will look like, all right? So this is the Galactic Center, this is the galactic disk, all right? So any region which is black, that means there is no emission. This red thing you see there at the blob, that's bright emission of 511 keV photons. You see there's this bulge, right? This spherical thing, and then there's a disk, right? So we see 511 keV photons in the bulge and in the disk, right? And this is, I mean, it has already been 50 years. It was first discovered by Johnson et al. In 1972. This is 2022, 50 years of discovery. And this is almost certainly not an instrumental effect. It cannot be an instrumental effect. Like various instruments using various techniques found this 511 keV photons, right? Integral actually has nailed it in great detail. It's unbelievable details, right? So the question is obviously, what is the source of this radiation? So Integral also measured the bulge spectrum, that is the bulge, that is this spherical region, bulge, and the disk, right? Disk is the disk region, right? So you can plot the flux versus energy. The flux versus energy. Say for the bulge, you see the 511 keV, this is the thing, all right? And for the disk. And it turns out that the fluxes are similar, right? Well, it's not exactly the same, but they are similar, right? Very similar fluxes, all right? So that means there's something which is producing this 511 keV gamma ray line. What is it? We don't know the answer, okay? So first question you can ask is, I mean, what is this 511 keV line coming from? right? Is it some new particle which is just emitting 2 511 keV photons, or is it coming from positron annihilation, right? And this is the one of the results which Integral nailed down. Integral found out that this is coming from positron annihilation, not due to a new particle producing 2 photons, right? This was an important result. So the idea behind this is if you have very low energy positrons, before annihilating, low energy means roughly say few MeV, 3-4 MeV. Before annihilating, they will form a bound state with the electron. All right. They can form a parapositronium, L equal to 0, or orthopositronium with L equal to 1. Right. If they form a parapositronium, they will annihilate and produce 2 photons back to back. If they produce orthopositronium, they'll produce 3 photons. All right. So you can calculate, and this is guaranteed. All right. So for 2 photons, you'll get a line, this one, and for 3 photons, you'll get this continuum. All right. So if this 511 keV line is due to Galactic Center positron injection, then you should not only see the line, you should also see the continuum. Now let me come to my previous slide. I'll show you. So you see, I told you this line, right? Huge bright line. You see there's a continuum also. You see this dotted line. If you see this thing, this dotted line, and this thing, right? There's a thing. This is the gamma ray continuum. You see gamma ray continuum. Right? So there's a line and there's a continuum in the bulge and in the disk. You see, this is the continuum here. There's a very, the continuum is less bright in the disk, but it's still there. There's a line and a continuum. And from quantum mechanics, you can calculate what is the fraction of producing line and fraction producing continuum. You do it from quantum mechanics. And this exactly matches here. So Integral told you that there's something injecting lots of positrons at the galactic center. What is it? We don't know. All right. So people also use gamma ray measurements at higher energies, greater than 511 keV, to help constrain the injection energy. What is the maximum energy with which positrons are injected in the galactic center? All right. It turns out roughly few MeV. Few is 3, 4, 5 at the most. Right. Not 20 MeV, for example. Not 10 MeV. Even 10 MeV is certainly good. It's few 3, 4, 5 MeV. So in the galactic center. All right. So okay. So the question is, there's something injecting lots of positrons at the galactic center at low energies. What is it? We don't know. Obviously, there are lots of models, like lots of astrophysical models. If you think of a dark sector, or exact dark sector, the simplest constraint that you can do, this is the only equation in my slide probably. It says that you cannot inject more positrons than what is allowed. All right. So forget astrophysics. So the 511 keV photons and the continuum gamma rays tells you something, we don't know what, is injecting 10 power 43 positrons at the galactic center. 2 times 10 power 43 positrons at the galactic center. Whatever, if you have a propose a new source, it cannot produce more than these positrons. That's it. Absolutely the simplest thing. So this is the thing, basically my paper is basically a division. So this is the equation. Basically, this is the total number of positrons per unit time, per unit energy. I integrate over the relevant energy range. This is the dark matter density. This is the mass of the black hole. You integrate over the volume. So this is the total number of black holes in that volume. And this is the fraction of dark matter in the form of primordial black holes. Right? You divide this, you get a constraint of FDM as a function of MP, which is as simple as that. Right? So if you know particle dark matter, you realize this is exactly like decaying dark matter. The formula is exactly the same. Right? However, there are some uncertainties. All right? How do positrons propagate? How do low energy positrons propagate? That is something we don't know, by the way, very well. What is the dark matter density profile? Again, we don't know it very well. Right? So these introduce uncertainties, and I'll show you what these uncertainties are. So this is my first result. What is being plotted on the x-axis is the MPBH. What is being plotted on the y-axis is the fraction of dark matter in the form of PBH. So this is the gamma ray constraint, this dotted line, gamma ray constraint. Right? Anything above this line is ruled out. Right? This is the CMB constraint. There's a CMB constraint which I did not talk about. I can tell you later. This is a CMB constraint. And these are the Voyager constraints, these cosmic ray constraints. Right? So anything above is ruled out. So the story is, if low energy primordial black holes exist, they will produce E plus E minus pairs. The positrons will lose energy, become non-relativistic, and annihilate with the ambient electrons to produce photons. Right? And that is the constraint. Right? We have a constraint on the number of positrons in the galactic center, injecting the galactic bulge. Right? So from that, right? So this is what I'm saying, requiring that the number of positrons on the PBH is less than the positrons that are required to produce the 511 keV line, and the low energy continuum, we put a constraint. Right? Assuming that the D and DM, that is number of black holes per unit mass, is a delta function, we get this constraint. All right. So depending on what is the black hole, what is the dark matter density, whether it's isothermal or NFW, And depending on how much the positron propagates from its birth position, does it propagate a small distance or does it propagate a large distance, we get this band of constraints. All right. So you see, you probe new parts of the parameter space. Right? You probe new parts of the parameter space here. Right. So this was this paper 1906-09994. Right. I must say that concurrently, same time as me, William D. Rocco and Peter Graham also wrote a paper. It's also published in PRL, the same back to back. Right. They got the same idea. I must also say that we are not the first ones to talk about this. Neither me nor Peter Graham are the first ones to talk about it. Lord Martin Rees wrote something very similar to this even before at least I was born. Right, so it's a very old idea, but then we just made it into in a new context. Recently, there's also another paper by Hooper who basically followed our analysis and tried to do the same thing. Right, Keith and Hooper. Right. In fact, yesterday there's another paper is very related. Right, I'll tell you what that is. All right, is this clear? This is probably end of one part of my talk. Is this clear? Are there any questions? Okay, right. Probably proceed. So the question is, after this, I said, how do you probe even higher masses, right? So this is coming from measurement of galactic center photons. So this is a work done in collaboration with Julian Munoz and Francis Latier, published in PRD. So this also, funny, sorry, this somehow got cut off, I don't know why. Anyways, so this gamma ray measurements of the cosmic electron and positron. Right. So this is again a measurement of integral. So here, integral wanted to know what is the high energy cosmic ray electron and positron density at the galactic center, right? In the galactic region, galactic center region, right? But high energy means few GeV. Right? That's what. So obviously you can't go and measure it. What you do is you calculate the energy loss of these electrons and positrons in the form of gamma rays and X-rays, and then you try to infer the electron and positron density. Right? So this is in this paper in Busho et al. Right? It's an extremely detailed paper. It's pure astrophysics, but it's extremely detailed paper, extremely well written paper. So they are measuring again the gamma ray emission in the inner galaxy, and then from that calculating what is the contribution of cosmic ray electrons and positrons. It's a long paper. The result is as follows. All right, let me explain these plots. What is plotted? So they divide the sky into various latitude and longitude beams. Depending on this latitude, minus 6.5 degree plus 6.5 degree. All right, what you plot the flux as a function of the longitude here. All right, for various energy bins, 27 to 49, 14 to 90, 100 to like this. All right, and then for the highest energies, you just do a different binning, right, in longitude. These are the data points. All right, these crosses are the data points in each of these things. You can do the same thing where you take a longitude bin and you plot the flux against latitude. Right, you get this thing. All right, these are data points. Right, also this one. So they did a detailed analysis and found that the data can be well described by inverse Compton emission, stellar emission, emission from stars, and annihilation radiation. That is the 511K. Once you include this, you can reasonably explain it, and that gives you some confidence that we understand cosmic electrons and positrons. Remember, these are electrons and positrons at a few GeV. But now we can use this measurement, this flux, to constrain primordial black holes. All right, this is what we did. Sorry, this is what we did. We reproduced this. We just plotted this thing: flux on the x-axis, longitude on the y-axis for a given latitude in this energy bin. This is the dotted flux. Right? This is the dotted flux, and the red circles are the predictions from PBHs. These red circles. Right, and the simplest thing we say is these emission should not overproduce this data set. All right, we went over all of these things. For example, if you take 1.5 times 10 power 17 grams between 200 to 600 keV in this band in longitude less than 23 degrees and latitude, you see this overproduces it. Right, this is the data this overproduces. Right. So using this, we found a constraint on primordial black holes, right? So I must say that this paper also contains a constraint on MEV dark matter. This paper of us by Munoz, Latier, and me, which I think is improvement of the earlier paper by Essig et al. All right, and I think because we take into account the error bars more precisely than what Essig et al does. All right. Anyways, so we did the simplest thing, just that the data points, sorry, the flux should not exceed the data points, right? In fact, we said that if you can model the signal and background, you can get an even stronger constraint. And this was actually done very recently, last month, two months ago by Bedford et al. In this 2202 paper. 220 people. Right. Anyways, so I'll tell you our constraints. Again, what is plotted on the x-axis is the MPBH. What is plotted on the y-axis is the fraction of dark matter in the form of PBH. Right. So these are the Voyager. This is the Voyager constraint. We just plotted one of them. The CMB, the external gamma ray, and this is the 511 kV constraint. This is the weakest constraint. 511 kV was a band, but I just plotted the weakest constraint, because we are trying to be conservative. Using this integral measurement, we get this line, this solid line. Anything above is ruled out. All right. Ignore this dotted thing. All right. So this is something technical, and let's ignore this. Right. So you see again, we probe new parts of the parameter space. All right. So beyond what 511 kV can probe. Right. Or Galactic Center positrons can probe. This is one of the best probes of low mass primordial black holes. This is relatively insensitive to dark matter profile. Right. This assumes a non-spinning monochromatic mass function of dark matter of PBHs, but you can also do it. After our paper, a similar paper was done by using the Comptel measurement by Stefano Profumo's group, Kuban et al., where they get slightly stronger constraints than us, very slightly stronger constraints than us. Right? But it's sort of complementary. Okay, good. So then next we come to the question, how do we probe even higher PBH masses? So currently, I mean, till now, there is no proposal of how to do, say, how to discover 10 power 18 gram black hole. Nobody has any idea, right? Turns out that there are very near future experiments coming up, proposed telescopes, we can do this. This is this paper led by Anupam Rai, Julian Munoz, and Regina Caputo, where we showed the near future EMIT telescopes, which are being proposed either in Europe or US. They can probe new parts of parameter space. The idea is very similar again, but these are new instruments. So these can look at better fluxes. So you just calculate the fluxes of coming from PBHs near the galactic center, in the galactic inner galaxy region, and then you just calculate what are the constraints you get. Right. So this is the thing. Right. So this is for monochromatic mass function. What is plotted on the x-axis is the MPBH. It's plotted on the y-axis is the fraction of dark matter in the form of PBHs. This is the weakest Voyager constraint, IGRB, the weakest 511 kV constraint, and the integral constraint. This is the Comptel constraint. It's slightly stronger, as I told you, from the Stefano Profumo's group. And we showed that if the black holes have zero spin at birth, then this is the region which it can constrain or discover. AMEGO. So AMEGO is a proposed telescope by NASA. It's still under consideration. This is it. If it has a higher spin, then it probes the even larger parameter space. All right. If it's a log normal, you can probe even larger masses. So you can see using this, say the monochromatic, you probe 10 power 18 grams black hole. All right. This work, the very similar work was also done in the paper by Kugan et al. Right, and then Ghosh et al. In this paper. Actually, only yesterday there was a paper by Dan Hooper where they did a very similar thing using E-astrogram. Right. In all of these things, basically we are showing that near future MEP telescopes, which one of them will be built for sure, by the way. All right. So sorry, this is projections. This again got cut off. I don't know. It was fine. The team. Anyway, one of them must be built. One of them will be built, right? Because MEP telescopes have not been built for a long time, right? And then you can discover PBHs if they exist in new parts of parameter space. There are no constraints, right?
Is AMEGO is proposed experiment?
Yes. AMEGO is a proposed experiment by NASA. E-astrogram is a proposed experiment by ESA. And then this Ghosh et al., this 2110 paper was using a experiment called XGIS Thews. So that is an experiment, proposed experiment by ESA, right? So MEP telescopes have not been built for a long time. So the last one was basically, you can see this Comptel. This is built in 1980s, in the 1890s, right? So we are, so many people are proposing it, and we are showing this is one of the test cases. All right. Okay, there are also other probes which I'll not talk about of low mass primordial black holes. But low mass is, as you can see, 10 power 16, 17, 18 grams roughly. You can use the 21 centimeter measurements. All right. So this is a recent work I did with one of my students, Akash Kumar Shah. She got accepted in PRD only yesterday. You can show that using the 21 centimeter measurements. So this is this plot, right? It's a very busy plot. Let's not go over all of this. If you're interested, I can tell you some details. But this band, you see the gray band, is something that you can get from 21 centimeter measurements, right? It's gray band, right? So we have many more results in the paper. You can look into it. So this can probe new parts of parameter space. You can have LEOT. LEOT is a dwarf galaxy. I mean, and depending on, and measuring how the dog galaxy is getting heated up, you can get a constraint. This is a weaker constraint, right? So this is this constraint, this black solid line. Right? This is a weaker compared to say CMB and the IGRB, the MEV, the paper, all my older papers is a slightly weaker constraint, right? It's also this paper by Kim, who claims it's actually slightly stronger, right? Because I think the way we study the propagation is actually slightly different between our paper and their paper. And then you can also have it by radio observations, right? Synchrotron and inverse component energy loss of electrons, positrons, right? There's many papers on this, right? So overall, this is a very exciting field. There are lots of papers coming up, and hopefully at some point we'll discover it. So let me conclude. So I hope I've been able to convince you that primordial black holes are a well-motivated candidate for dark matter, right? There are large regions of parameter space where PBHs can make up 100% of dark matter density, and there are even larger positions, even larger portions of the parameter space where PBHs can make a very large fraction of the dark matter density, say 10% or even more. The observation of the low energy positrons, the galactic center, via the 511 keV and the associated continuum gamma ray photons gives you a very strong constraint. This I showed you earlier in the one of the parts of the talk. Showed you the measurement of galactic center photons can give an equally strong constraint. And then near future telescopes like AMEGO can probe new parts of the parameter space. And the other probes include dwarf galaxy heating or 21 centimeter emission and even others. So as I said, it's very important for primordial black holes to probe the entire parameter space to as small a cosmic density as possible. As I said, even if you find a primordial black hole which makes up less than 1% of the dark matter density of the universe, that's new physics, guaranteed. Right? There's no way astrophysics can do it. Hence, I think it's an important thing, and one should probably try to probe it. So this is so I end my talk. So if you have any questions or comments, please feel free to. So my email is listed. Please feel free to send me an email, and I'll be happy to talk. Okay, thank you.
Thank you very much for your nice talk. So now it's time for a question or comment. So is there any question or comment?
In your earlier talk, you
Sorry, what? I can't hear you.
You cannot hear me?
Yeah, my voice is somehow breaking up. Sorry.
I see. Can you hear me?
Yes, now I can hear you.
I see. Thank you very much. In your earlier talk, you consider the signal of positron from black hole emission and after the photon from black hole emission separately for constraint.
Yes, you're talking of this thing, right? This part.
Yeah.
Yes.
Yes. Yes.
Yes. What is the question?
Yeah. So if you combine these two signals, can you get more constraint? If you combine these two signals, if you
Sorry,
combine the,
if I combine the voice,
if you combine these two signals,
which signal?
for example, yeah, if you combine the two signals, for example, for 511 kilo electron volt, if you combine not only the positron but also photon from the black hole emission, and for photon, yeah, and also for the photon analysis, if you combine the positron electron analyzation to the photon constraint.
Yes. So this is So this is just talking of the positron constraints. The photon constraint is this one, this part. So this part is a photon. This paper is a photon constraint. So here we are assuming that black holes are producing photons, right? And then you should not overproduce these measurements. This measurement, these measurements. So this is just purely photon. So here I am assuming black holes are producing photons. All right. And then we get this constraint, this black line. This is a photon constraint.
Right? But positron also make the photon from the annihilation with electron.
Annihilation with electron, yes. So yes. So turns out, yes. So what you can do is, for example, I think this is what I say. So you are producing these positrons, and these positrons will annihilate with electrons and produce photons, right? That is a weaker constraint, by the way. That is you get a constraint, but that is a bit weaker constraint.
So that adding these two signals in your analysis doesn't make change.
Sorry, what?
So adding these two signals in your analysis doesn't make change the result.
Sorry, I cannot understand this. Can somebody repeat? Sorry, I'm sorry. Please.
Yeah. Sorry. So adding these two signals doesn't change your result.
Yes, correct. Yes, this signal does not. Yeah, it doesn't change the results. Yeah, you can do it, but it's a bit weaker constraint. So if you take positrons, these are positive, just analytic. It's a bit weaker constraint, but it doesn't change the result substantially.
Thank you very much.
Thanks. Sorry, I couldn't understand it. My fault.
Sorry.
Is there any other question?
I have a question. Can you distinguish between normal particle decaying dark matter and primordial black hole?
Yes. That is easy. Remember, if you have primordial black hole, right? So suppose so the question is, suppose you find a signal, right? What is it? Decaying dark matter or primordial black hole? The point is basically this spectrum. This spectrum is sort of like black body, and as you know, like, it's incredibly difficult to produce this spectrum from particle dark matter decay. Right. So if you compare the spectrum very precisely, actually not even precisely, like for example, if you get the signal slightly less than MeV, right? I mean, the particle dark matter can only decay to photons. It can't produce E plus E minus, right? So if you get the spectrum, you can cleanly distinguish it. It's not a problem.
But in the case of charged particles, you need to take into account the propagation of the charged particles, then maybe the original spectrum might change. I don't know.
Yes. So that is the problem, for example, with this constraint from Baudal and Chirelli. So here they're actually measuring E plus E minus. Technically, when I'm saying positron, I'm not measuring the positron. I'm saying the positron is doing something and then it's producing the 511 kV and lower energy photons. That's what I'm doing. Yeah. So it can change it slightly, but I think still you can distinguish it. Knowing this thing. Remember, and the idea is as follows, right? So the initial spectrum that is being produced of charged particles due to particle dark matter and primordial black holes are different, right? Then it is getting scrambled up in magnetic field diffusion, all of those things, right? But the initial condition is different. So I think you can sort of try to get into the initial conditions, right? By inverting this thing, and you can distinguish it. There is some hope to distinguish it.
I see.
The other thing is, for example, remember, for example, as I told you, for low mass primordial black holes, there are lots of various constraints, right? So you can use various different messengers to probe this thing. That also comes something can be done.
I saw that some Myunjung was raising hand, right?
Yeah, there was a hand up.
There was a hand somewhere.
Yeah.
Yes.
Yeah, go ahead.
Okay, thank you. I have a question. Then the black holes are heavier than the other dark matter candidates, right?
Yes.
So I want to know how many black holes you expect in one galaxies, and they will be very large, and the number of the black holes will less than the other candidates. So where they will be inside the galaxy?
Yes. Okay. So first of all, so the question is, how many black holes do I expect? Primordial black holes do I expect inside a galaxy? Right? So that depends on what is the mass, right? So the Milky Way mass, let's think of the Milky Way, is 10 power 12 solar mass. So I am talking of, say, this constraint, 10 power 17 grams, which is roughly 10 power minus 13 solar mass, right? So then if black holes are of this mass, 10 power 17 grams, then there are 13, 12, then the 10 power 25 black holes in the Milky Way. All right, 10 power 25 is a large number. All right, so yeah, obviously particle dark matter are much more numerous, but 10 power 25 is a large number. So I think there is not much, effect due to that.
How many black holes in the cola bottle? It's normally for WIMP dark matter.
For WIMP dark matter.
Yeah, we said 1 liter cola bottle. Take the one kilowatt 1 liter, you have few of them.
Yes.
In the case of primal black hole, how many of them?
Yeah, that I have to calculate, right? So it's 0.3 GeV per cubic centimeter, right? Local. So, so one solar mass is 10 power 57 GeV. All right. So these are 10 power. So let's think of 10 power 17 grams. So this is 10 power minus 13 solar mass. So that is 10 power 44 GeV, right? So yes, you require 10 power 43 centimeter cubed to have one black hole. The number is extremely low, but it's still large enough. When people do these simulations with primordial black holes, we can think of it as a fluid. This number is large enough, by the way.
I see.
Yeah. So even for one solar mass, you can think of it as a fluid, by the way. So then there are 10 power 12 10 power 12 black holes in the Milky Way. You can still think of it like a fluid. It's not a problem.
Adriana, do you have a question?
Yes, I was curious about if these limits are actually sensitive to primordial black holes clusterings, or if it's robust to this too.
Sorry, what is sensitive?
To the clustering of PBH.
This limits. Oh, good. That's a very good question. Yes. So I think the clustering of PBHs change the lensing constraints, and there have been lots of controversy in the literature. But I think this, because clustering means many primordial black holes forming together, right? But and then that changes whether the lensing geometry works or not, whether objects are like two objects are like this, few objects like this, or they're all bunched together. So that changes lensing. So these constraints are not changed by lensing. Because remember, this is just counting and just how many, whether they are bunched like this or they are bunched like this. As long as it is inside my observational volume, it will emit black Hawking radiation. So yeah, so these constraints do not depend. So one of the advantages, these constraints do not depend on the clustering properties of the primordial black hole.
Okay, thank you.
Thanks. Yeah, thanks for the question.
Is there any other question?
Is it possible to explain 511 keV from primordial black hole evaporation? No.
Yes.
Right? Yes. No. No.
So, so I think I would say the answer is no. Yes,
no.
So recently, there's some paper by Hooper. I'll tell you why. Okay, it's an incredible coincidence. Let me tell you why. There's just one map will tell you why. This is the map of 511 keV. Right? Any dark matter cannot produce this map to 0th order, right? Because dark matter is spherically symmetric. The dark matter profile is spherically symmetric, right? It cannot have a disk component. So then you have to say that there is some astrophysics which is producing the 511 keV at the disk. And coincidentally, that astrophysics is not present in the galactic bulge. As primordial black holes are producing the dark matter at the galactic bulge. Sorry, this 511 keV in the galactic bulge, right? It can happen, fine. I mean, I cannot say that it cannot happen, but it's an incredible coincidence, according to me. Also, the other thing you can show is that the dark matter profile that you require to explain this, right, is not NFW. It has to be R power minus 1.6, not R power minus 1. I have not seen any simulation which tells you that the profile is R power minus 1.6. It's very, very difficult to produce that. So yeah, so I would say answer is no. But as I said, I mean, actually, only yesterday Dan Hooper had a paper where he's claiming to it, but then he doesn't say what is producing the positrons at the disk and why is the morphology not matching. The morphology is completely off, right? This is not the morphology of dark matter. Right? Dark matter is spherical. You must have seen this, right? Spherical shells, right? Yeah. So it's a coincidence. So I think my argument is the answer is no. But okay, maybe there's a coincidence.
I didn't know about this spectrum. You have 511 kV gamma ray lines from both bulge and the disk.
Yes, exactly. So you see,
so if it is from the bulge, maybe it is from dark matter annihilation and it's spherical.
Yes, but then you have to say how come we don't see it? How come there's also exactly something similar which is producing it at a disk?
Right.
That's a coincidence, right? That's a problem, right?
It's a general problem for the dark matter interpretation.
Yes.
Right?
Correct. Yeah. Any dark matter interpretation of 511 keV. Now, actually, earlier, for example, before Integral did this bulge and disk analysis, it was okay because actually the bulge, as you can see, this is brighter, right? This was easily seen. But now that you have it in a disk, it's incredibly unlikely to produce dark matter. In fact, there are many papers, even recent papers, where they talk about how stars can reproduce this morphology. There's stars at the bulge and stars at this. So stars can reproduce. Means actually stars means supernova, by the way. So it can reproduce this, right? But dark matter, well, okay, maybe it can, but I think to zero authority that doesn't look like dark matter.
I see. Yeah. Thank you.
Any other question?
Sorry, again, can you hear me?
Yes, yes.
Thank you very much. Dark matter, if they are unknown particles, dark matter also can emit these unknown particles.
Yes, yes.
Then the fraction to the standard model particle can be changed if the energy, the number of dark matter emission is the same. Can this change the result?
Yes, for example, no, okay. Well, overall density is obviously not changed that much, but it does change. For example, when we find this, I don't know if you know about this, there's this positron excess measured by Pamela and AMS, right? So that is telling you there is more, and if that is due to dark matter, I don't know, well, I think it's probably not due to dark matter, it's probably due to pulsars, but if that is due to dark matter, that is telling you some more standard model particles which dark matter is producing over known astrophysics. Yeah, so it can change slightly, but not very much. Can't change. Yeah, it can't change very much. Yeah. Because remember, all of this dark matter annihilation, decay, with this primordial black hole evaporation, these are very weak processes. Right? These happen very, very slowly. These don't happen very often. Right? So that's why the overall number density of standard model particles do not change due to dark matter interactions. Okay, roughly do not change. Yeah, technically you're right. There's some change, but that change is very minor. So for example, you can ask this question. Let me do this. Due to dark matter annihilation or decay, does this 4.9% become 5%? You can ask this question, right? It's more standard model particles. Yeah, that is very, very little. Because dark matter does not, I mean, first of all, we are assuming that dark matter is annihilating or decaying. We don't know, right? But even if it annihilates or decays, that change is very little because it's a very weak process. It doesn't happen often. And it's happening only in galaxies, not in, and most of the universe is not galaxies. Most of the universe is just empty. There, the dark matter density is even less. So that doesn't happen. Right? So you look at this picture, these are galaxies. So most of the dark matter annihilation, if it happens, is happening in these galaxies. But in the black regions, where most of the universe is very less density of dark matter. I mean, orders of magnitude less density of dark matter. So there, the dark matter annihilation is not happening. Hence, there's not much change to this 4.9% number. Is this clear?
Yeah, I'm wondering if the unknown particle there, the fraction of the standard model particle becomes smaller from the dark matter evaporation. Yeah, I just if the dark matter total energy of the emission is the same, if there are unknown particle emission, because the energy fraction, the unknown particle also have so that the energy fraction. Yeah.
So you're talking of something which converts ordinary matter to dark matter, right? Is that the question? Some process, say for example. Is that right?
Yeah.
Hello.
Maybe. Ordinary dark matter.
Hello.
Hello. Can you hear me? Yeah. I mean, energy fraction of the visible particle becomes smaller if the dark matter run away the energy.
Sorry, I lost the internet connection. I could not hear what you said. Can you repeat?
Yeah.
My internet connection.
I mean that if the unknown particle has the energy fraction.
Yes.
Of if the black hole, the total energy of the black hole evaporation is the same.
Yes.
If the unknown particle has the energy of the partial fraction, then the invisible particle having the smaller energy or smaller amount of the small amount of the evaporation.
Yes.
The number of the evaporation. Yeah.
Oh, so you're talking of suppose in black hole evaporation, it's producing also new particles, right? Beyond standard.
Yeah.
Okay,
and then
good. So that can happen. In fact, recently there are many works, for example, trying to do leptogenesis or baryogenesis using black hole evaporation. That can happen. But remember, this emission, that I'm talking about just depends on the spin of the particle and the mass of the particle. So even if you produce new particles, this overall thing does not really change. Right? This rate may change because because there is some the answer is this rate does not change that much, because this rate only depends on the spin of the particle and the mass of the particle that is being produced. If the mass and the spin are different, then it will change. But for a given photon, right, even if you produce a right-handed neutrinos to do leptogenesis, this number will not, this fraction will not change, because that is a different particle. The particle with different spin and with different mass. So that will not change the photon emission for it. Is that clear?
I see. No problem. I see. Thank you very much.
Yeah, sorry, I lost the internet in the middle. Sorry.
Thank you very much.
Yeah. So yeah, you can look into the papers by, there are many papers by somebody in Jessica Turner. She has done lots of works on leptogenesis, either leptogenesis or baryogenesis using black hole evaporation, primordial black hole evaporation. You can look at that. She has done very good works. So there you can see. But again, the masses and spins can be different, so it then does not matter.
Thank you very much.
Okay, thanks. Yeah, thanks for the question.
Any other question or comment? I have a small question.
Yes.
I want to, if any, I want to understand the connection between your constraint and some inflation models. Can we say, can we say something about model building of inflation?
Good.
From,
okay. Good. That is the part I have not done. To be honest, I'm not an expert on inflation. But that, I think what you do, actually there are many papers which do these things, and they use, I mean, my results, other people's results. What you have to do is to find, say, let's take up this result. So to figure out some inflationary model which will produce 10 power 14 kilograms or 10 power 17 grams black hole with some density. Then you can constrain it, right? So yes, so this constraint is, I would say, is what I say is more model independent. It does not depend on what is producing the primordial black hole. But you can obviously do the other reverse process, like knowing the density of the primordial black hole as a function of mass, you can constrain inflationary parameters. And this is done in many papers. If you want, just send me a message and I'll send you how people do it. Just invert the problem. Then that can constrain some parameter space of inflation.
So in the first figure, you showed there are two regions we can fully explain dark matter from PBH, right?
Yes, yeah.
In both regions, we have how to say? Can we make inflation model to?
Yes.
Okay.
Yeah, there are many models. That's not a problem. There are many models, inflationary models, which can produce 100% of dark matter density, and they typically put it here, right? There are also some models. Sorry, just one second. There are also models which put some fraction here, some large fraction, and some fraction say for here to explain the LIGO results, for example. Yeah, that can be done. Yeah.
And your constraint is relevant for the left allowed region, right? Like.
Yeah, my constraint is somewhere here. So here, it's somewhere here. Yeah, it's slightly beyond this extragalactic gamma ray constraint. It was slightly here, say for example.
Okay, thank you.
I think most inflation models are focusing on the lightest primordial black hole, because there's the constraint from the number of foldings. The heavier dark matter, I think you are producing it because it's the short radius is small for heavier dark matter. Sorry, it's larger. Sorry, it's larger. Sorry, so they must be produced in early time during inflation. So I think so then there's more constraint.
Yeah, most of the models are actually in this range because there are zero constraints here. As I said, there's nothing. So you can make as much as
for inflation model side.
Yes.
Because the larger the black hole mass, the larger shield radius.
Yes.
That the larger scales will exit horizon in the early time. So you need the large perturbations in the early time. That means even actually there's constraint on the number of wavefoldings. You want to have a standard slower inflation for a certain period. At some point, you change it to produce a large perturbation. So that period will be shifted to early time if you want to produce heavier black holes. So I think mostly we are focusing on the barely allowed region to the left, far left, that you are barely evaporating, but you are not really evaporating.
Okay, thank you. Yeah, that's
so it's interesting. I think that there are some work on this, but as you said, there are a lot of papers. Yes.
Yeah, there's almost one paper every day nowadays.
Yeah. But also there might be some other ways to produce primordial black holes. So I don't know, just yeah, it'll be interesting to distinguish, but I don't know how to distinguish.
Yes, that is difficult. Yeah, because in the end you just get the mass and the spin of the black hole. That's it. You don't get anything. That's a problem.
I don't know if you have something else together with the primordial black holes. It might
sometimes people do it.
Easily distinguishable.
No, sometimes people do it. For example, while producing the primordial black hole, you can also produce the stochastic gravitational wave background. So this is production, not merger, production process. And there are people who talk about how you can have a primordial black hole in, say, for example, in this range, this low mass range, and you can say, for example, produce stochastic gravitational wave background at some frequency which can be detected.
I see. Okay.
So that is like a sort of multi-messenger way to search primordial black holes.
I see. It sounds more interesting. Yes.
Yes. Yeah. So even for I think nanograph results, people have done this.
Right. Nanograph.
Yeah, I think those black holes are heavier. They are in the solar mass region. I think at least some of the models that I looked into, they are solar mass.
Okay.
Okay. Thank you for the discussion. If there is no further question, let me thank the speaker again. Thank you very much.
Well, thank you. Yeah, thanks for all the questions.